السلام عليكم. طيب بنتابع مواضيع بالديناميكا الحرارية. راح نحكي عن جيبس فري انرجي اند equilibria. جيبس هو عالم أمريكي بسنة 1875. وضع هاي نظريته اللي هي الفري انرجي اند equilibria. all طبعا هاي بتحكي عن الكيميكال سيستم. All chemical system tends naturally toward state of minimum gaps of energy free energy. إذا طاقة جيبس الحرة، وهي جيبس بتساوي اللي هي H minus T S, where is the G is Gibbs free energy and H enthalpy or heat content, T is temperature in Kelvin, and S is entropy. So entropy can think of as randoms. So Gibbs free energy هي عبارة is energy that is still useful رغم إنها يعني ظهرت ب 1875. So a chemical reaction will occur if the Gibbs would decreases. So Gibbs free energy also known as the free enthalpy اللي هي heat content. So is a thermodynamic potential that measure the maximum or reversible work, and we know what is the reversible work that may be performed by a system at constant temperature and pressure. And when we have constant temperature and constant pressure, this means we have isothermal for constant temperature and isobaric for constant pressure. So spontaneous and Gibbs free energy. Gibbs free energy is measure of the spontaneity of a process. Delta G is the change of the Gibbs is the free energy change for reaction under state conditions. A constant temperature and pressure, delta G equal delta H minus T في delta S. And if we increase in delta S leads كل ما زدنا دلتا S هذا يعني راح يكون في عندي نقصان بدلتا G because here is minus. Okay. So if delta G less than 0, this means the forward reaction is spontaneous. And if delta G greater than 0, the forward reaction is non-spontaneous. And we know what you mean by spontaneous process. And if delta G equals 0, the process in this case is in equilibrium. So the Gibbs free energy is generally agreed to be the weapon of choice for describing a chemical reactions and equilibrium between phases. So it is defined as G equal H minus Ts, and in this case, what's H? If we substitute the equation instead of H, enthalpy, so which equal U زائد BV minus TC. So where H is enthalpy and U is the total internal energy and T its absolute temperature and S is entropy. So if we take dG, this means we have to take du زائد bdv زائد vdb minus tds minus sdt. Remember that here we take du زائد bdv زائد vdb, and because we have two variables. So remember that thermodynamic variables come in pairs. So one is intrinsic, does not depend on the system size. ده بيكون داخلي. أو the other is extrinsic, خارجي, depends on system size. ومن الإكزامبل pressure, الفوليوم, temperature and entropy. So also G and N, the number of moles of stuff in the system. هون لازم نفهم إنه hence G is appropriate variable when material is moving between phases. إذا G is appropriate variables إذا إيش تحركنا من phase إلى phase. Another equations about uh, Clapeyron's equation. From the first law of thermodynamics we know that du بتساوي T ds minus B dV, since the change of entropy ds equal dq by dt, so S equal qt, but for ds we have dq by t, and the mechanical work done on the system when it is expands. This means minus BdV. And if we substitute into this equation, so dg equal du زائد bdv زائد vdp ناقص tds minus sdt. This leaves to dg equal minus s dt زائد vdb. In a closed system, the mean contains a pure substance, vapor, condensed phase. Okay, this phase coexist in equilibrium. So write the free energy equation twice, once for each phase. In this case, one for vapor and one for condensed phase. So for condensed dgc تساوي minus sdt زائد vcdb, and c is referred to the condensed phase. dgv equal minus sv dt زائد v v vapor dB, and v, this refers to the vapor phase. إذا free energy is the same in both phases, اللي هي G condense تساوي G vapor. Change in free energy when some independent variable is changed must be the same if they are remains in equilibrium. This means dgc تساوي dgv. Again, we put this equation together. minus SCDT زائد VCDB تساوي minus SVDT زائد V VDB. And we take for dt, and here is dt, ناخدها عامل مشترك SV minus SCDT تساوي V للفيبر minus V للكوندنس dB. This is here. This side is related to the temperature, and here related to the pressure. So S vapor minus S condense is the entropy change that takes place when material moves from the condensed phase to the vapor phase. And we know the change of the entropy, which equal delta Q over T, where delta Q is the amount of heat required per mole of material moved between two phases. And delta Q is just the heat of vaporization. So again, the equation, the enthalpy U زائد PV تساوي Q, or dB by dt تساوي delta S over delta V, and this is Clapeyron equation. It's related the change in pressure of vapor to the temperature enclosed. Okay, this is related change in the pressure of vapor to the temperature enclosed. Monocompounded system to the heat of vaporization. So system temperature and molar volume change the material on vaporization. So from equilibrium equations, we can calculate the phase diagram. For lack of better model, we treat most vapor as ideal gas, whose molar volume is given by V over N بتساوي RT over P. This is we have creating an ideal gas. Alternatively, equation of state is needed. Molar volume of gas is typically factor of 500 larger than condensed phase. Hence, V the condensed is negligible in comparison. And substitute and integrate. So this is gives B T تساوي B نوت exponential دلتا اتش في على R في واحد على T minus واحد على T نوت. And this is related the pressure as a function of temperature. So in this case, it depends on temperature. So the vapor pressure in equilibrium with a condensed phase increase exponentially, sort of exponential to minus 1 over t is not exactly an exponential, with temperature from 0 up to the critical temperature. And the deviation from linearly on if we make logarithmic plot, so temperature depends of the heat of vaporization, and the exponential minus 1 over t is not really linear in the exponent. So it's not linear. Okay. So heat of vaporization from CRC data logarithmic, if we take here vapor pressure in tour and temperature in C, so we can see this graph. Here equal the logarithmic, okay, equal minus 0.2185 A على T plus B. This is B, the intercept. So this is the end of this lecture, and also this is the end of the course on thermodynamic. So we will stop at this point in this topics, and next week we will discuss some problem in thermodynamic, third law, the entropy, enthalpy, and so on. So thank you for your attention.